Hi, this is Dr. David Hudson, and we're here with the second part of the first lecture for Introduction to Marine Science for the Non-Scientist. So the inspiration for this part of this is the background picture you're seeing, which is a staghorn coral reef in northern Colombia in the Caribbean Sea. This was of major importance because these are animals that actually put down rock, essentially. So let's get into talking a little bit about geology and plate tectonics and how that whole thing works. So first, let's talk about the ocean floor. There are 5 major ocean basins. The Pacific is the deepest, with the Marianas Trench at over 30,000 feet. We've got other major trenches and low points within the oceans, everything from the Java Trench at 24,000 feet. The trenches are from South Sandwich Island, around 24,000 feet as well. In Puerto Rico, there's the Puerto Rico Trench, which is 28,000 feet deep, and then up in the northern part of the northern hemisphere, off of Greenland, you've got Malloy Hole, which is 18,000 feet deep. So this is essentially the map of the ocean floor. You can see the oceanic and continental crust, and to think of this essentially as a floating crust on a molten mantle will help to understand what we're about to go through. So if we think about drilling down into the Earth's interior, you've got different layers within that. So you've got, obviously, if we think about even before we get to the surface of the Earth, the exosphere, the thermosphere, the mesosphere, the stratosphere, the troposphere in our atmosphere, and then we have, which is not to scale, and then we have the crust, the upper mantle, the lower mantle, the outer core, and the inner core as we go towards the center of the Earth. Now, if we were to think about that in a general perspective, and then think about the lithosphere as being the crust in the uppermost solid portion of the mantle, the oceanic portion of that is far thinner than the continental portion of it. So the crust is anywhere from 0 to 100 kilometers thick. Now, when we think about the continental crust, that is primarily made out of granite. It's lighter in color and it's light in density. And it tends to be between 10 and 30 miles thick. It's up to 3.8 billion years old, nearly the age of the Earth itself and about the age of our solar system. And then there's the oceanic crust, which is very heavy. It's darker, so it doesn't float as high up into the mantle. And it's about 3 miles thick, and it's only about 200 million years old, so it's quite young when we think about the age of the ocean floor. Now, this is all the result of centuries and even millennia worth of work. But as we think about these parameters, the ocean floor itself used to be quite different. So Alfred Wegener in 1912 started to try to think about how these were pieced together. He came up with this idea of looked at the count and said they just kind of pieced together a little bit here, and around 150 to 190 million years ago they were so that now what we ended up with is that he came up with this idea of continental drift, but couldn't really explain how Pangea broke apart. So okay, they were all one supercontinent at one point, but how did this break up? What were the processes, and what evidence is there for us to think about? Turns out part of this, as we're thinking about evidence, are the fact that we have similar rocks on each coast. So if you look at the fact that South America and Africa are the two most obvious ones, because they kind of still look like they piece together, we notice that they have similar rocks. They also have similar extinct fossils. So fossils that are containing some of the same Triassic animals are in bands of of these deposits across multiple continents, which is pretty incredible. When we think about rock formations themselves, so something beyond the rock composition and the fossil locations, but the rock formations themselves, if we look at the Laurasia and Gondwana when they broke apart, the current Appalachian Mountains actually extend into what are considered the Scottish Highlands and into what is now Europe. So we also see that the Atlas Mountains that are on the western coast of Africa were once aligned with that mountain range and split apart. So when we think about that, it's a really important piece to how all of that fit together. Now, certainly, as we're thinking about these rock formations, the Earth as it's formed new rock, as evidenced by earthquakes and volcanoes, the separation points where this has happened allow for what's called the spreading center. Well, that spreading center has also, which we find in the mid-Atlantic ridge and in any of these places where you have two plates moving apart, allows for new crust to form. So when that new crust forms, it's formed, all the atoms within and those molecules within that rock are aligned with the current Earth's magnetism. So the magnetosphere flips polarity from time to time, but as these rocks form, they are locked in. So we actually see bands moving away from these spreading centers where you have older and older rock as you get further from the spreading center, and we can go back and look at this registry and see the direction of the Earth's magnetic field at that time. So it's really interesting that they allow you to think about that magnetism that's there. So the theory that drives the continental drift is called plate tectonics, and what that allows us to think about is that these new tools that we had during World War II, we discovered the Mid-Atlantic Ridge, for instance, right after World War II because we had sonar and we were able to see that there are mountains down there. So that we noticed that there are these huge slabs of crust that are separating. And if we were to map this out for the age of that lithosphere, we've got very young crust along all of these areas in the lower left where you see in millions of years around these spreading centers, you have very young crust. As you get further away from those, you get older and older crust. Now, if we were to look at the directions that all these different plates are moving, it allows us to also think about how these things are moving around and where we would end up finding earthquakes. Thinking back to just where we would find earthquakes and thinking about what you just saw with the map of the plates, it turns out wherever we have plates interacting, we are more typically going to find earthquakes and volcanoes. So this is, there's a lot of friction and a lot of heat in these locations. So when crusts separate, they release leave a blanket of pressure which allows the hot mantle to rise up in between, and this causes seafloor spreading because if the plate moves over and new rock forms, it's not going to move back very easily. Now, earthquakes themselves, if we're thinking about tectonic activity, it's where there's a lot of friction. So an earthquake is essentially the result of a movement based on some built-up tension between two plates, and then all of a sudden it will jolt and move. So, but when we're thinking about the direction that these plates are moving, it's really important to consider that when it comes to what's occurring in these locations. So to think a little bit more about this, North America and the Eurasian plate are pulling apart and forming new crust in an ocean spreading center like we see in the middle here. It's about as fast as your fingernails grow, so it's very slow. But over geologic time, it forms new crust. So even over the course of your lifetime, you could consider that there's a fair amount of new crust formed during that time. However, there's certainly a subduction that can happen in locations as well, and that's where you're going to find some of the deepest places in the ocean. Those are convergent plate boundaries, and so at that point, one plate is going underneath another. You have rift zones in the middle of continents where you have actual separation of two plates or a continent that's pulling apart into two plates. That is a type of spreading center. And eventually you will end up with an ocean there. This is happening in Eastern Africa, for instance. You also have some hot spots and shield volcanoes that occur when the asthenosphere comes close to the surface. An example of this is in Hawaii, where you have the plate moving over a hot spot and new islands forming with each movement. So along the continental margins, we have a couple of different kinds of things that are happening. And just before I get to this, I want to just back up for a second. You have two types of boundaries here that are divergent or convergent, but you also can have a transform boundary where things are moving along one another. The example being California, where you have Baja California that's moving northward along that. So it's these are important for considerations when it comes to the buckling of the plates themselves. Now within this area, you do have movement from the lithosphere down into the asthenosphere and back up. So there is cyclic movement of this rock within these locations along these continental margins. But typically what you end up finding is that the areas that are subducting are considered our active margins. These are areas where we've got quite a bit happening, and these are areas that end up being the deepest, where you have an oceanic trench. Now the continental shelf and along the continental margins is going to be a little bit different on an active margin and a passive margin. If we're thinking about the coastal plain along the eastern United States, for instance, you can have a pretty large continental shelf. Continental slope isn't necessarily this steep, but it is considered the depths between 200 meters and 2,000 to 3,000 meters. Typically, the rise that we see after that is just sediment that's kind of fallen down the slope. You have an abyssal plain from 4,000 to 600,000 meters, and if you do have an oceanic trench, you have that portion. But the edge of the continental shelf is considered to be ended at the end of the continental slope. Now, the plain, that abyssal plain, which is between 10,000 and 16,500 feet deep, or 4,000 to 6,000 meters, is kind of dotted with volcanic activity depending on what's going on. When we think about these, I mentioned the continental margins being passive or active. We've got the passive margins here that are put through. We do have some that are volcanic passive margins, where you have some volcanic activity, but there's not a lot going on in these locations. You do still get, for instance, earthquakes in New York, but there's a very slow slope, so you get some sedimentation. You've got this this result from this mid-ocean ridge where you end up with a passive margin because all the action's happening in the ocean. So if you think about the passive margin off of South Carolina, you get the Blake Plateau, and what this looks like can be a little bit different, in different locations. But this is essentially how things look underwater, and again going down to 6,000 meters. So that nice wide shelf. But thinking back, okay, we've got an active margin. This is where we're going to have, rather than the thinking about the result of a divergent plate boundary that we saw in the mid-ocean ridge, where we have a transform plate boundary like you have here in California, where this is moving up to the northwest, or a convergent boundary like you have in where the Nazca Plate is going under South America, you get this very active volcanic activity and very active geologic activity. Thinking more closely about Long Island Sound and the east coast of the United States, you've got going back, just orienting ourselves here. You've got the state of Connecticut, Rhode Island off to the east, and New York off to the west and south, because Long Island is part of New York. Going back, there was a glacial formation over this location back in the Pleistocene about 1.8 million years ago. Around 86,000 to 2,000 years ago, the ice thickness was between 4,000 and 10,000 feet deep, so 1,000 to 3,000 meters deep. Around 19,000 years ago, those glaciers retreated and formed a recessional moraine, which we know as Long Island. That was a big bunch of sediment that was left there. Now, that left a freshwater lake, and as more glaciers around the world melted, the sea level rose, and that glacial lake was flooded by seawater, which we now call Long Island Sound. So the lake previous to that was called the Glacial Lake Hitchcock. Around 15,500 years ago, ocean levels rose to break into that lake, and by 13,500 years ago, it was a very well-established estuary. Now, around 9,000 years ago, First Nations were hunting in this area. 8,000 years ago, the sea levels were pretty close to the present day. In 1612 and 13, Adrian Block first sailed into this area. And 1632, the dust which the India Company purchased was now Old Saybrook, Connecticut, from Native Americans in that community. And if we think about the impact that even early human development had on Long Island Sound, this localized place in the eastern United States, 56% of the Connecticut population lives in a tidal community. So this is still a really important place for where humans live. It has a lot of challenges because of that, and it has a history of ongoing change because there are these changes that have occurred prior to having good baseline data. And with a high population on the coast, we've got a lot of engineering challenges to recovering some of the lost functions that we had. And some of that long-term legacy includes high nutrient loading, things like fertilizers and septic tanks and sewage treatment. We have over 69 streams that flow into Long Island Sound, which is a really incredible amount of input. Thinking about those major challenges and thinking again about how that geology impacts it, there's a lot of interchange with the open ocean in the eastern end of the Long Island Sound, whereas down in New York City, you have just the East River that does go out to the ocean. There are marine animals that come through the East River to get into eastern Long Island Sound. And the efforts that people have made to improve the inputs into Long Island Sound have resulted in some good changes to where the nutrient grades are getting better. The water quality sound-wide is getting better. We've got some additional issues for Long Island Sound, mainly around climate change. So we've got things like lobsters moving north and fishes moving into deeper waters that are colder. And we've got these other shifting species like blue crabs that are now all the way up into Maine and are regularly overwintering in places like Long Island Sound. So things are changing as these physical characters that are acting on the geology are changing. When we're thinking about sea level rise issues, these are areas that will likely get flooded with coastal flood risk. We've got historical dams that are slowly being brought down, but with invasive species in the area from other places that are adapted to very similar conditions, this can affect the recovery of these ecosystems. But all that said, there are some bright spots in the management of this. There's good management of aquaculture and coastal resources. This place has the Long Island Sound Interstate Aquatic Species Management Plan in place. The Connecticut Blue Plan was recently implemented as a framework for permitting projects around where we humans should be putting things, and allows us to make some better decisions. So the interplay between what's physically in a place and how things move and how water moves really affects the ecology of an area. It also really affects how humans use that space and how we can best be stewards of these places. Stay tuned for part 3. Thanks for watching. If you'd like to support us, please go to buy coffee at www.upwellcoffee.com or go to remoteecologist.org/support to donate to our nonprofit or to join us in the field on trips. Thanks so much.